Welcome to this deep dive, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. We are diving deep today into, well, one of the most critical topics from Unit 7, alternating current. We're looking at AC voltage applied to a Series LCR circuit.
This one always seems a bit daunting. So many formulas.
Exactly. But today we're going to break it down. We'll use some simple analogies, so simple that you will understand the core physics and, remember it for life. So let's start not with the formula, but with a question. Think about your car radio. You're driving, and there are hundreds of signals, radio waves from every station, all hitting your antenna at the same time.
Right, all at once.
So how does it do it? How does your radio, or your TV for that matter, know to pick out that one specific station signal and just ignore everything else?
I've never really thought about it like that. It does seem like a bit of a miracle. The input is just a mess of frequencies, but what comes out is one clean sound. It must be some kind of electrical sharpshooter.
That sharpshooter is a perfect way to describe it. And that mechanism is exactly what we call resonance, which happens inside an LCR circuit. But here's where it gets really surprising. A little counterintuitive, frankly. It's a phenomenon called voltage magnification.
Voltage magnification.
Yes. If we tune the circuit just right to its special resonant frequency, the voltage you measure across the inductor or the capacitor, well, it can become dramatically larger than the voltage you are supplying from the source.
Wait, what?
I mean, it can be 10, 50, even 100 times larger.
That can't be right. We're talking about a series circuit. Voltage is supposed to get divided, not multiplied. How can one component have more voltage than the entire source? That seems to, violate everything we've learned.
Absolutely. And understanding the paradox is at the heart of today's deep dive. But first, we need to build the foundation. So the core idea is this. We have three components in a line. A resistor, R, an inductor, L, and a capacitor, C, all connected to an AC source.
Okay, R, L, and C in series.
Right. Now, R is simple. But L and C, they don't just oppose the current, they also shift its phase. They are constantly fighting each other. So the main question is, what is the net opposition? The total pushback that the current feels from all three. We call this total opposition. Impedance, given by the letter Z.
So impedance is like the equivalent resistance, but for an AC circuit with all three components.
Precisely. Let's use an analogy to make this super clear. Let's call it the three-person tug of war.
Okay.
Imagine the current is the motion of the rope. Person R, the resistor, is pulling straight ahead, in line with the rope's motion. He's like friction, always taking energy out.
Simple enough.
Now, person L, the inductor, and person C, the capacitor, they are the tricky ones. They pull sideways at a 90-degree angle to the rope's motion.
Sideways?
Yes.
Yeah.
And crucially, they pull in exact opposite directions to each other. One pulls straight up, the other pulls straight down.
Hold on. Why exactly opposite? Why 180 degrees apart from each other?
Ah, that is the most important part. It comes down to phase. Remember our mnemonic? Civil?
Civil. Yes, in a capacitor, current leads voltage. And in an inductor, voltage leads current.
Exactly. So if the current is our reference, the inductor's voltage is 90 degrees ahead, or up, and the capacitor's voltage is 90 degrees behind, or down.
So one is plus 90, the other is minus 90. The difference between them is 180 degrees.
Okay, got it.
They are in direct opposition.
Perfect. So the total opposition, the impedance Z, is the combined result of the straight pull from R and the net vertical pull from L and C fighting each other. This gives us our mental image.
The impedance triangle.
The impedance triangle.
Yes, picture a right-angled triangle. The base, the horizontal part, is the resistance, R, that's fixed. The vertical side is the distance between the pull of L and C, so it's XL minus XC.
Okay, base is R, height is the difference in reactance.
And the hypotenuse, that's your impedance Z. The total resultant opposition. Now, if we want the current to be maximum, we need this opposition Z to be
minimum, as small as possible.
And how do you make that hypotenuse as small as possible? You make the vertical side 0, you make XL equal to XC, then the triangle just collapses onto its base.
You've got it. The hypotenuse Z becomes equal to the base R. That's the condition for resonance. Okay, let's bring in the formal insert wording now. Could you read out the exact formula for impedance Z?
Yes. The formal definition says the impedance Z is equal to the square root of R squared plus, in brackets, XL minus XC squared.
Excellent. So Z equals root of R squared plus the net reactance squared. It's just the Pythagorean theorem applied to our triangle.
Right.
And of course, XL is the inductive reactance, omega L. It increases with frequency. And XC is the capacitive reactance, 1 by omega C. It decreases as frequency goes up.
This inverse relationship is why they fight.
Exactly. And the derivation is just 4 quick steps. 1, you start with Kirchhoff's voltage law, but for phasors. So V squared equals VR squared plus, in brackets, VL minus VC squared.
So we add the voltages vectorially.
Yes. Step 2, you substitute Ohm's law for each part. V equals I times opposition. So VR is IR, VL is IXL, and so on. The total V is IZ.
Okay, so we get IZ squared equals IR squared plus all that.
Step 3, you put it all into the equation. And step 4, since I, the current, is the same everywhere in a series circuit, you can just cancel out the I squared from every term.
And we're left with the formula for Z. Z equals square root of R squared plus XL minus XC squared.
Perfect. Now, that formula gives us the magnitude of the opposition. But what about the direction? That's the phase angle. Phi, from our triangle, tan of phi is just opposite over adjacent.
So tan phi would be XL minus XC, all divided by R.
And that angle tells you everything. If XL is bigger, phi is positive, the circuit is inductive. If XC is bigger, phi is negative, it's capacitive. And if they are equal,
Then the numerator is 0. So tan phi is 0, which means phi is 0.
and we have resonance. The circuit behaves as if it's purely resistive. The L and C have, perfectly vanished in terms of phase. This happens at the resonant frequency omega naught, which is 1 by root LC. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Okay, so let's get back to that astonishing fact. Voltage magnification. We said VL or VC can be huge at resonance.
I'm still stuck on that. If the total current is just I equals V by R at resonance,
Yeah.
how can VL, which is I times XL, be so big?
Yeah.
XL would have to be enormous.
And it is. That's the key. The factor that describes this is called the quality factor, or Q factor.
The Q factor.
The Q factor is simply the ratio. It's the voltage across L or C divided by the source voltage. So Q is VL over V.
Okay.
And if we substitute the formulas, VL is I times XL, and V is I times R at resonance. The I cancels out. So the Q factor is just XL divided by R.
The ratio of reactance to resistance.
Exactly. So if you have a circuit with very high reactance and very low resistance, the Q factor can be very large. A Q factor of 50 means the voltage across L and C is 50 times the source voltage.
Yeah.
This is what your radio does. A high Q circuit is a great tuner.
So low resistance is key to getting high voltage magnification.
Absolutely. Let's do a quick example. Say we have R equals 10 ohms and the source voltage is 200 volts.
Okay.
And let's say at resonance, XL and XC are both, let's say 80 ohms.
Right. XL equals XC equals 80.
So at resonance, Z is just R. It's 10 ohms. The current is maximum 200 volts divided by 10 ohms. That's 20 amperes.
20 amps. That's a lot of current.
It is. Now check the voltage across the inductor. VL is I times XL. That's 20 amps times 80 ohms.
That's 1600 volts.
1600 volts. From a 200 volt source, the Q factor here is XL over R, which is 80 by 10. It's 8. And you see 8 times the source voltage of 200 is 1600. It works perfectly.
Wow. Okay. Seeing the numbers makes it real. The voltages are huge, but they're equal and opposite, so they just cancel out for the total calculation.
You've nailed it. Now, that phase angle phi we talked about, it's the key to the next concept, which is power factor.
Power factor.
Yes. In AC, the power you supply is V times I, but the actual useful power, the power that does work, is VI times cosine of phi.
So cos phi is the factor that determines how much of the supplied power is actually used.
Precisely. We call cos phi the power factor. If phi is large, like 90 degrees, cos phi is 0. You have current flowing, but 0 power is consumed. It's called wattless current.
Wattless current.
Yes, it just sloshes back and forth, doing no useful work. But at resonance, phi is 0. What is cos of 0?
1.
1. The power factor is maximum. All the power supplied is used by the resistor. A circuit is perfectly efficient. Okay, now for the most important part for exams, the silent killers, the misconceptions that cost students marks.
Right.
Misconception number 1, students write that at resonance, the resistance R becomes 0.
Ah, I can see why they'd think that.
But it's wrong. It's the net reactance, XL minus XC, that becomes 0. The impedance Z becomes minimum equal to R. But R itself is still there, limiting the current. If R became 0, the current would be infinite.
Right. That makes sense. The resistance is the only thing left stopping the current. It doesn't disappear.
Exactly. Now, misconception number 2 goes back to the voltage. Students think that because XL equals XC, The voltages VL and VC must also be 0.
We just proved that's not true with the 1600-volt example.
Right. But the confusion is understandable. The key is that their vector sum is 0. VL plus VC is 0. But individually, they are massive. The tug of war is a perfect stalemate, but the tension on the rope is immense.
So I should remember it like this. The individual voltages VL and VC are at their peak, but they cancel each other out in the overall circuit calculation because they are 180 degrees out of phase.
That is the perfect way to state it. Okay, let's give you some memory hooks to lock this all in.
Okay, good.
For resonance, remember this phrase. Resonance is when the capacitor and inductor make a peace treaty, leaving the resistor alone.
Chuckles. A peace treaty. I like that. They stop fighting.
Yes, they cancel out, and R is all that's left. For phase relationships, we already have our mnemonic civil, C-I-V-I-L. It covers everything.
Right, civil.
And a physical gesture. To remember the voltage cancellation, hold your left arm straight up. That's VNL. Now hold your right arm straight down. That's VC.
Okay, up and down.
At resonance, their lengths, their magnitudes are equal. They are perfectly opposite. So when you add them up, what do you get?
Nothing. 0.
Exactly. A perfect cancellation. Okay, let's wrap this up with a quick, exam-safe 3-point summary. Point number 1. The total opposition in a series LCR circuit is called impedance, Z, and it's calculated by the phasor sum. Z equals the square root of R squared plus XL minus XC squared. Point number 2. Resonance happens at a specific frequency, omega naught equals 1 by root LC, where the inductive reactance XL exactly equals the capacitive reactance XC. And number 3. At resonance, the impedance is minimum, Z equals R, the current is maximum, and the circuit acts purely resistive with a phase angle of 0 and a power factor of 1. To get maximum marks in 12th CBSE Physics, Chemistry, and Math, visit ProfSam.com.
That is P-R-O-F Sam, right?
Yes, ProfSam.com.
Thank you for joining us on this deep dive into the LCR circuit. We really hope you feel much more confident about these concepts now. And before we go, a final thought. We talked about the power factor, cos phi. Now, if you run a large factory, you are using a lot of inductive motors. Your power factor will be low.
Right, because of all the inductors. So you're drawing a lot of that wattless current. It doesn't do any work for you, but it still flows through the power lines, heating them up, causing losses for the electricity company.
Ah, so they are supplying current that isn't being used effectively.
Exactly. So think about this. Why do electricity boards charge heavy penalties to industries if their power factor is too low? And why do these factories install huge banks of capacitors? We'll leave that real-world economic consequence for you to think about.